representation theory. And slightly more specifically, I study the representation theory of Lie groups. So what representation theory is it's more of a language. It's a tool for studying symmetry. And Lie groups are a certain type of symmetry. So symmetry is something that we all sort of understand. We have some notion of what it means to be symmetric in the world. For example, a butterfly is symmetric because the patterns on one side of its wing align with the patterns on the other side of its wing when it flaps its wings. So a butterfly has a reflective symmetry across this axis through its body. And what I do is I study these types of symmetries using a certain mathematical language.
Is in sort of the intersection of two fields, algebra and topology. And I kind of think about various different types of projects, but most of them are in the field of knot theory. I think about braids, which are a specific type of configuration of a knot. The various things I like to think about is how can you represent a braid in a more sort of mathematical, tangible way. So I would call that a representation. So you take braids and sort of change them into something else. And that something else I think about is a matrix. So that might be like a grid of numbers or a grid of polynomials. And that kind of feels a little more traditionally mathematical. So we can study these matrices as a way to study the braids. And that's kind of the foundation of the research I do. A lot of the properties about braids that we care about are sort of, can we faithfully represent braids in this new format, these format of matrices? So what does that mean? What is a faithful representation? So braids have a mathematical structure to them. So if we're thinking about braids as like ropes in the air that are tangled and tied up, and they start at the top and they tangle and then they end at the bottom. You can make new braids by taking two braids and then stacking them on top of each other. So you can make a longer braid. And there's certain properties that happen within these braids. So sort of if you allow the strands to blow in the wind, the crossing information and the way that it looks might change, but we still have the same braid there. Just might have a different sort of configuration that you blow on it. And so these types of properties that we're looking at are algebraic properties. So to say we have a faithful representation is to say that all of these matrices that we're dealing with capture all of the properties of the braids that we started with, just sort of in a new format. And every braid gets sent to a different matrix. And so we can, if we want to study different braids, they have different matrices that go along with them. And so I mainly answer questions about this sort of translation process, not so much about the braids themselves, but about the process by which we're translating them into this other object. And so faithfulness is kind of the major motivating question that I study.
So early in the early 19th century, physicists were starting to realize that the descriptions they had of the physical world were not quite matching what they were observing in their experiments once microscopy got stronger and they could see things at a smaller level. And so about this point in time, physicists were developing theories to describe what was happening on the molecular level. So individual atoms and things, how these could be modeled physically. They developed a physical theory to describe it, and this was the theory of quantum mechanics. And at the time, this was very strange, the idea that there could be these discrete changes, but it was observed over a period of experiments, and this led multiple physicists from different directions to develop these theories of quantum mechanics. And I'm not a physicist, I'm a mathematician, but it turns out that you can predict some of these strange phenomena if you just use the fact that a system is symmetric. So if we take maybe the very simplest quantum system, which is a single hydrogen atom, and we do some sort of experiment to test something about this atom. So maybe we shoot it with a laser and see what happens. What I see from this angle, I should be able to draw some conclusion about what's happening in the experiment. And what you see from this angle, you should be able to see the experiment happening as well, and you should be able to draw the same conclusion. And so what this is saying is that if you and I can both watch the experiment and draw the same conclusion from different angles, the entire system has a symmetry. It has a spherical symmetry. And it turns out that by using this, we can make predictions about how the system has to behave that match with these experimental predictions that physicists saw back in the 1940s. I think it plays really nicely to the interaction between mathematics and physics.
So ionic liquid is a salt. It's a pure salt, but it's a liquid at room temperature. And it's a liquid at room temperature because there's a mismatch in the size of the positive ions and the negative ions. One's much larger than the other. So a good friend of mine is a physical chemist, and she did some experiments and observed that when you put a droplet of ionic liquid on a flat substrate, what happens is there's a very thin film that spreads outwards from the droplet. And she can look at the thickness or the height of these thin film using AFM equipment. And what she found is that if you put a certain ionic liquid on a certain substrate, you would get different kinds of patterns. So different ionic liquids make different patterns. Some of them look like leopard spots, some of them look like giraffes, some look like zebras. Now, some of these patterns are very useful for lubrication, and some of these patterns are not useful at all for lubrication. And at the moment, they don't know how to tell which kinds of ionic liquids will make a pattern that's useful for lubrication and which ones won't. So there's millions of ionic liquids, and choosing the right one is not easy. And the current models, so they're very computationally difficult. And so when I saw these patterns and I saw that they look like animal skins, I thought maybe we can use the same kind of models that are used for animal skins. These kind of things are often modeled with reaction diffusion equations, which are the same kind of equations that I've spent a lot of time solving.
So I was taking a class as an undergraduate on differential geometry, and the teacher gave us a lot of freedom into what we could do our final project on. And a friend and I decided we wanted to design a bicycle that could run smoothly down the stairs. So what we came up with was this flower shape, which was the complement to the stairs. It was a great project. It had some really beautiful and fun math, and it was also just kind of a quirky thing to figure out. But recently, last year, I was contacted by Randall Munroe, who is the author of the comic XKCD, and he was writing a new book called How To, about curiosities in the world and how to do ridiculous things. And he had stumbled upon this project that I had done back as an undergraduate, and he was so excited to see it because it was exactly the same thing that he was trying to derive for something that he was working on in this book. And now there's a very cute little comic of our flower-wheeled bicycle showing up in this new book by Randall Munroe.
I tend to stay on the very sort of theoretical side of mathematics, but the way that I kind of see how math fits in the world is I kind of see like mathematicians are kind of like miners or something. We're digging the tunnels, like digging. We don't really know what we're looking for, but we're digging and we're just pushing the edges, pushing the boundaries. We have no idea what's useful. And then the physicists and the biologists and the chemists and the engineers will sort of discover some sort of property about the world. And then they'll call down the miners, the mathematicians at the bottom, and saying, hey, we discovered this thing. Do you have any mathematical model that studies that? And then we look in our bag and we're like, oh yeah, about 15 years ago, we solved this thing. Does that help? And then we kind of just hand them the models that are useful.
So my path was not so intentional to mathematics. I really did not think I was going to be a mathematician when I was young. I grew up in the Western United States in a pretty small town, so I didn't know any mathematicians. I always liked math, but I thought that it was a little bit boring actually, and it didn't really capture my imagination very much. But when I started university, I had no idea what I wanted to study. And so I wrote down on this form that I was going to study math, and I intended to change my major later actually. I assumed that I would change it. But then I never did. So I started university and I started taking these math classes. And the more classes I took, the more beautiful it got. And suddenly I realized for the first time that it didn't have to be algorithmic. So I started taking these classes where we'd study these interesting objects in multiple dimensions and we'd prove things. And suddenly it didn't feel like I was just following a set of rules anymore. It felt like it was something creative and beautiful and like I was exploring. And so I started really enjoying math. And so towards the end of my undergraduate degree, I had professors reach out to me and say, oh, well, have you thought about going to graduate school? And then it was really in graduate school that when I started doing mathematics research for the first time, that I realized what a good fit this was for me. And I finished my PhD, and now I'm continuing down this path, being a mathematician. So it was a little bit of an accident, but a happy accident. Very happy to have ended up here. So careers in mathematics are sort of funny. I didn't know this when I was getting into it either, that they have a lot of stages. So your first stage is to finish a bachelor's degree, which I did, and then in the United States, you go straight from bachelor's degree to a PhD, and then you finish a PhD. And then when you finish a PhD, you don't automatically become a professor. After this, there are a few intermediary phases, and that's where I am right now. So I'm currently a postdoctoral researcher, and I'm on a two-year position. And then after this, I will complete another postdoctoral position. So this will be another temporary position at a different university. And after this, I will apply for permanent positions somewhere. And so once I've done these temporary positions, these will set me up in a good position to be able to develop my own research program and settle down somewhere permanently. And this structure of mathematics is a little bit wild because it has you moving all over the world every few years, but it's also very exciting. It gives you this great opportunity to move to different parts of the world and interact with different people and learn their perspectives of math. And then once you've collected all these different perspectives, then you're at a stage where you can settle down in your permanent home and become a professor and build a program with students and postdocs and kind of develop your own sense of mathematics. Mathematics has the wonderful quality of being a very international world, and so it's hard to know where you'll end up. There's active mathematics in my research area all over the world and lots of exciting people to talk to.
I have been a dancer my whole life. In fact, until I was 18 or so, I thought I was going to be a singer and a dancer on Broadway. And then I found mathematics and my life went in a different direction. But I love performing, I love dancing, I love being on the stage. And until a couple years ago, math and dance were just very separate parts of my life. I did not see a way how math and dance could be related or could be joined. They felt very separate, and so my life just felt very divided. So I ended up making an aerial dance video about my research, and I won the competition, so that was really exciting. My career has been forever changed. I will always be thinking about how can I turn my research into dance, and that will just always be an avenue of my work.
I like to do math very collaboratively, and in general, I think a lot of mathematicians do this as well. Math is a very social thing. Math gets done by talking. It doesn't really get done by sitting alone and thinking so often. Most of the most productive times are when you're talking to somebody else or working on a project with somebody else.
Basically, all you need is your brain and a pencil and you can do math. And so I think some people really enjoy doing it on their own, and then some people, like me, are more social. So I think there's kind of a place for lots of different types of people and personalities in research.